So we're going to be 3 people doing this instrument session. Starting today, it's going to be mostly theoretical, like the principle of detection of LISA. From the strain to the observables, we're going to have in LISA and up to TDI. Tomorrow is going to be Ada, talking more about hardware aspects of this detector, like hardware aspects of heterodyne interferometry, plus optical bench, and that kind of things. And on Friday, it's going to be more like post-processing, sensitivity of LISA, noise properties by Olaf Hartwig, and a bit of also of TDI. Okay, today is going to be some math, so be ready for it. I'm going to do stuff on the blackboard for 45 minutes. I'm going to do a short introduction of, astronomy with space-based detector, and also what are the challenge to have access to this milliyear span. And then we're going to run to the math. Okay. There's going to be some sounds also, because I like to convert, waves and bit note into sound. I think it's pretty cool. You have a QR code here where you have more material. So they might be an hands-on session on Friday or maybe later next week. There's some material you can check out here and have a prepared content environment if some tools are used next week or on Friday. But you can have a look. All right. Okay, but first I like to start my lecture usually with this slide. So like with LISA, we're not going to detect a radiation wave. I mean, it's not the point. The point is to actually build an astronomy with it. I mean, of course, the radiation wave is interesting because you can check whether GR is correct, the number of polarizations, propagation speed, and things. But I think what we're very much interested in is like the sources, the mechanism of the sources, the dynamics, the formation channel of these sources, how they're distributed in the universe, what are the mass, the spins, and so on. And also, so we're going to mainly focus on the source we know, and we have a good clue that exists. But of course, we could also open the access of unknown astrophysics. And so really the point of LISA and gravitational detector is to open a brand new astronomy. And I think a good example is this GW 1708-17. So this is a very important date, first because it was birthday of Jean-Baptiste, and second because of these neutron star binary systems. It's a very good example of astronomy because it kicked off the multi-messenger astronomy with like electromagnetic counterparts to a gravitational wave. And so with that, we could, there's a lot of science made out of it. First, we could check that propagation speed of gravitational waves was indeed traveling at the speed of light. So it ruled out many of the scalar tensor theory where it was not the case. Also, for the very first time, it proved experimentally that some of the short GRB we see are actually connected with kilonova and merger of binary neutron stars. And also, like many other results, like for instance, the nucleosynthesis of heavy atoms beyond iron, which are also proved in that kind of signature. So in the center, you see a typical spectrogram. So again, I converted the sound because that's funny. So so it's typical chirp you heard with LIGO Virgo detector. And also in extremity, you have the one from Virgo. Right, that's it. Yeah. Almost. Yeah, so the thing is, so we're opening a new astronomy, and as electromagnetic like astronomy, this is multi-wavelengths. So ESA has already like a lot of mission to explore this electromagnetic universe from the microwave spectrum up to infrared visible, like with Euclid or JWST, James Webb, up to even integrals of the gamma ray spectrum. But okay, so it's going to be exactly the same with gravitational waves. And here, in our case, we have, at the moment, basically 3 detectors, project detectors. Some are already functioning. Some are going to be launched in 10 years. So we're going to have PTA for the nanohertz band. So basically, the lower frequency, the more heavy the objects you're going to have a look, you're going to observe, and the more far away they're going to be also. And so with PTA, you basically see some of the golden source of LISA, but at a very inspiral phase. So you see like typical the object above 10 to the 7 solar masses. So the LIGO Virgo detectors, they see high frequency parts, so they typically see stellar mass scale objects merging. And LISA stands right in between. So it's going to be in the millions band, where you see a large variety of sources. That's very interesting because you see stellar mass black hole at the spiral phase. You see also a massive black hole binary, which are at the merger phase, so the same source as the PTA, like maybe slightly lighter, but it's the same kind of sources. You see also MRIs, so this is a schematic system. You have a stellar mass black hole plunging on a supermassive black hole. So really, you have a very diverse type of astrophysics, and that's why this milliards band is very interesting to check. So it's very interesting, very rich in astrophysics, but it's very hard to open. Yes, okay, so here you see typically the sensitivity curve of LISA and all the zoology of sources you can have inbound. So currently at KU11, I'm working on something called DDPC. So this is preparation of the ground segment of LISA, and the problem is, imagine you have all these sources at the same time inbound for 2 years. You have like billion of galactic binaries, hundreds of families, and so on. So the challenge is, well, how to disentangle all these sources and isolate and can study them separately. So we're currently preparing the ground segment for that highly challenging problems. And we're cooking up what we call Morito dataset. So we like to name simulated dataset after our course, because this is like a complex cocktail where you put all the ingredients. And to give you an example, in Morito, we are preparing 20 massive black hole mergers along 2 years of simulation, 8 MRAs. We're going to have millions of galactic binaries. We're going to have 8 stellar mass black hole, and we're going to have possibly stochastic background, all at the same time during 2 years dataset. And it's a simple one, because in the future we're going to have even more. So this typically gives you a glance of what we could expect in the LISA band. Okay. So this milliards band is very rich, but it's also very complex to open it. And the two major problems we have is, first, we need to deploy an interferometer which has typically the scale, 2.5 billion of kilometer scales to be able to be sensitive to these very large wavelengths. And also we need to get free from terrestrial noise, because you know that at low frequency, seismic motion, neutron noise affect a lot sensitivity, so you have no choice but to go to space. Okay. Typically, the principle of detection is very simple. You basically try to reproduce a very naive picture of representing a gravitational wave by the formation of a ring of free particles. But as free particles, you have now satellites, and not only they need to freely fall, but you need also to monitor the length, varying lengths between them. And so that's what you need to build in space. So this interferometry system monitoring the variation of the separation between the free-falling spacecraft. Two problems. First, the spacecraft are not really free-falling, because they're like exposed to many noise sources, force noise, solar noise, thruster noise, and so on. So you need to find a way to make them in practice free-falling. And we use a test mass inside the spacecraft, which is very approximate, very close to be free-falling, because we protect as much as possible it from the spurious forces. And also, you need to realize this very long baseline interferometry, so we're talking about 2.5 million of kilometer travel of the laser across the constellation. And by definition, it's going to be an unequal arm interferometry, because the arm lengths are set by what are your orbits. And so then your Michelson scheme, where you have like the same path length on both sides to cancel the noise, is no longer available, so you need to find another way. This animation was made by Ricardo here, who is in the room, and nicely show, the orbit, the motion of the constellation, the cartwheel motion of the constellation. So there are realistic orbits here. Yes. Okay. So the first challenge was like to make this test mass free-falling, and that's what actually was a dedicated mission led by ESA in order to show that. So you basically take one arm of LISA, you shrink it into a single spacecraft. So the test mass now are separated by like a couple of tens of centimeters. And of course, you're not sensitive to gravitational wave because the arm is too short, so the effect of the wave is going to be super small. But you're sensitive to the relative acceleration noise between the test mass, which are basically, the deviation for a pure free fall, and that's if you have too much noise, it's going to deteriorate your sensitivity in LISA. So you want to make sure that the relative acceleration between this test mass and this test mass that you monitor with an optical path here, going through the optical bench, is compatible, is as high enough sensitivity to measure gravitational waves. So that's what we did, and it worked beautifully. I think even better than expected, which is rare. Yes, so I participated to the data analysis of this mission. It was during my PhD actually, and well, not only we wanted to check whether the acceleration noise was low enough, but also we wanted to understand what's the physical origin of this. And so if we could extrapolate the result of LISA Pathfinder to what it would be for LISA. So we wanted very to understand the origin of this noise. And so there was some, like a set of experiments, like trying to, excite one of the perturber, like temperature or magnetic field with a sinus, inject a sinusoid, for instance, and see how the acceleration of the test mass was reacting. And we were able to measure what was the contribution of magnetic field, contribution of stray electrostatics from the test mass, and so on. And we built a noise budget for LISA that now is used to define the sensitivity of the instrument. Why it worked beautifully, I think there was two main novelty compared to state of the art. So there was also other accelerometers in space that were used for observation of the Earth mainly. But this one really made like a big step. So it was 2 orders of magnitude improvement in the sensitivity. And the two main aspects was, first, we're using interferometry in space. So it was the first time we did optical metrology system in space. So we had a sub-picometer, I think it's even below 10⁻30 meter per square rooters sensitivity for measuring the displacement between the two test masses. It was very striking. So that was new. And of course, and an important one also, so a major source of noise is when you have an electrostatic charge buildup of the test mass, which gets then exposed to a stray electrostatic field around the test mass and create a force noise. That's a major problem for that kind of setup. So usually there is a golden wire that connects the test mass to a mass, to evacuate the charge of electrostatic on the spacecraft. And because you have this mechanical contact at low frequency, it's kind of damping the test mass and make it deviate for pure free fall. And you were basically losing sensitivity, adding some acceleration noise. With the Pathfinder, we did not do that. So the concept was we're going to use photoelectric effect. So we're going to illuminate the test mass with UV, and we're going to pull the electrons without any mechanical contact. So it was new. I think it was a kind of a risk, a novelty, but it worked beautifully. And it gained us 2 orders of magnitude at low frequency of acceleration noise. That was a big step. Now, all the metrology missions are interested to use that new method. All right. What else? Yeah, okay. So as I said, so also we were shaking the spectrograph in all directions to see what was the coupling to the test mass and stiffness or cross coupling between the channels. And there was a lot of experiment involved. So here are the results. The acceleration noise, so that's not the end results. Yeah, I put this one because this was interesting, so you can have a glance of what was the noise hunting. So you see the noise progressively getting down with some investigation we made. So between the red and the blue, you have basically the difference is that there was a coupling of the acceleration noise between the two test mass, what we call the differential mode. So there was acceleration between two test mass. Normally should be independent of whatever the satellite does. There is no mechanical contact with the satellite. It was not perfectly true. There was some residual dynamical connection between the motion of the spacecraft and the differential acceleration of the two test masses, mostly rotational to longitudinal. But because we measured well the rotation of the satellite, we were able to cross-correlate the noisy motion of the satellite with impact on the acceleration noise between the two test masses, both at low frequency, there was a force coupling, and at high frequency was a longitudinal sensing coupling, and which is now associated with TTL in LISA. We have called tilt-to-length coupling, where you get coupling between noisy spacecraft rotation and your long arm sensitivity, and that we were able to suppress. Probably the same will happen for LISA. But in LISA, of course, because of what we will see time delay, interferometry, all post-processing chance. This kind of correction is going to be a bit more tricky. The origin of this noise, this flat noise floor, is basically due to Brownian noise. So around the test mass are protected into vacuum chamber. Again, they're disconnected mechanically from the spacecraft. They're free floating inside. But this vacuum is not perfect. So there's some residual gas. And this residual gas, there's some atom like colliding the test mass randomly, and it goes random motion of the test mass. And that's responsible for this limitation noise floor here. And we, yeah.
Quick question.
Yeah.
So I was just thinking about that. Like, you have all these. You have a casing for the spacecraft, and then you got your test masses, which is inside another place.
Yeah.
And there's outgassing. Does that not happen effectively? Why can't you just open up? I don't know how it works in space.
That's exactly what we do. Yes.
Okay.
So it was vented. Exactly so. There was some gas vacuum made before launch, I believe, but it was not perfect. And then once settled in position in operation, the vacuum chamber were connected with outer space, and the gas was vented out.
And there's still
so
some
that's
residue?
why you see progressively, months after months, we saw this Brownian noise getting down as the pressure was like lowering. So that's why also we knew that it was actually Brownian noise. Also the relation with temperature also was very consistent with the Brownian noise.
Okay.
So that's why here between basically April 2016 and February 2017, time was playing for us and just makes the sensitivity better until you reach that level. Yeah. We still have some excess at low frequency. Part is due to the fact that, around the test mass there is a set of electrodes which render possible the fact we can control the test mass in case there is a drift of test mass inside the vacuum chamber. We tried as much as possible in the sensitive axis to don't act anything because it should be free falling. But these electrodes on this axis are also used for rotating the test mass because we want that to be also aligned with the inner walls. And this voltage you apply can have some noise and then lead to some force noise at low frequency. So part of this thing is due to that. Part is not understood. So it's part of what you call mystery noise, and it's still under. So we have budgeted that for LISA, but it's still not perfectly understood. And the big ramp up here, you see higher frequency is just sensing noise. So your sensing gets less sensitive at very high frequency. Second challenge. So that was partly covered, mostly covered by LISA Pathfinder. So that's why also. So the good thing is this first detection of LIGO and Pathfinder was almost at the same time. So the field was like everybody was excited. So I guess it participated to the enthusiasm for LISA as well. Yes, and the second part is that we didn't test for LISA with LISA Pathfinder, is the fact that these test mass to test mass measurements are not 20 centimeters apart, but they're 2.5 million of kilometers apart, which makes something a bit different. And so, yes, and you need that because you need to have a large effective deformation to be sensitive to more low frequency. And there are several problems. First, yes, so we have on board 1 watt laser power to be emitted to the distant spacecraft, but because of divergence of the beam, what is received is a few hundred picowatts, and so you cannot just bounce back with a mirror to the spacecraft. So you're going to end up to Planck scale. So you need to copy this phase and to send another. So you have another local laser at the distant spacecraft. You can copy the incoming phase and send it back with another 1 watt power. So it's what we call a transporter scheme. So it's not exactly a direct mirroring, but like a copy and sending back. Yes, and an important point is that the orbits are unequal and time varying, and exactly, I mean, you don't know them exactly. We have model and we're going to have ephemeris for the orbits, but it's not known perfectly. Right. So which means that, in traditional Michelson scheme, what you do, basically, so it's one that you learn at school, you have one laser source, and so this laser can have frequency noise quite noisy, I mean, quite large. But as long as, so you split this laser beam, as long as they travel exactly the same optical path on both arms, the noise stays coherent. So when you make interference at local spacecrafts, both frequency noise cancel out. If you have a big difference on the arm, it's no longer true. So you end up with like a noise which prevents from your detection of your gravitational waves. So you need to find a solution for that. Okay. And this is time delay interferometry. So what you can do is, like, instead of making direct interference, of your two left arm and right arm in the local spacecraft, you can measure. First, what we do is not exactly Michelson interferometry. We do interior-die interferometry. We're going to see that at the end. So we make interfere slightly different frequencies. And when you sum these two signals, they create a beat note. So you're going to have a low frequency part and a large frequency part. The low frequency part modulating the high frequency signal. And what you're going to measure is the phase of this beat note. Okay. So you're going to have 6 beat notes in total across the constellation. And you're going to make the interferometer on ground. So you're going to download all this data. And you're going to synchronize all these beat notes so that you have the equivalent of an equal alarm interferometer. Okay, so you're going to delay all the data stream, and you're going to be able to recombine, make a combination of your measurements so that the laser node is suppressed. This is TDI. This is not only important for that, but it's also important to combine also the test maps, because, as I said, the spacecraft, they are noisy, so they also affect the frequency you receive. But because they house a test mass which is super quiet, they can lock the trajectory on the test mass, and so effectively be as quiet as the test mass. But you're going to have a measurement of the motion of the spacecraft relative to the test mass, plus a relative measurement between the two spacecraft. And you compose all these measurements to both suppress the laser noise and also the spacecraft noise motion. That's the point of TDI. We're going to see that later in more details. Yeah. You need the box.
So this red path, just to be clear, so this is is this the only path that can solve this?
No, and this one actually is a known one. It's 1.5 TDI. It's not correctly accounting for the fact that you have a brazing constellation. So yes. So we have the correct one. You do several round trip across the arm. It's more difficult to picture. That's why I didn't put this one.
But so these guys are supposed to be what you said, like you go back to like classical microsecond scheme where the noise is coherent and will cancel out.
Yes. So you basically make constructing artificially like the laser was going through a path, and make sure that you have like two same paths will make the same length in total, and you make them combine, so you guaranteed. So you have laser node which is cancelled. It's really software interferometry. Okay, so let's. So what's the introduction? So now we're gonna try to derive one of these Y here, so one of these beat nodes. So so basically, what we're gonna do, we're gonna measure frequency. So we're gonna sit in one of the spacecraft, and we're gonna receive the laser frequency of the distant spacecraft and compare with the local, and see that everything that happened in between the spacecraft, like propagation effect, like the velocity, relative velocities that induce some Doppler effects, or the waves that pass in between, it's going to modify the frequency you receive, and your end observable is going to be observed frequency from the distant spacecraft minus the emitted frequency over the emitted frequency. And this quantity is going to contain the wave you want to measure. All right. So let's have a look here. So this is this setup. We're going to focus on a single arm. This guy is going to send a frequency to this guy here. So before, at emission, you're going to have a frequency. At reception, you're going to see a different frequency, as I said, because of Doppler effect along the line of sight plus the Greenwich waves. And the difference is going to be observable. So the way I'm deriving it is based on this paper that Tom is the co-author of. He's really expert on that, actually. And so, but we're going to do a simpler version of it. So we're going to basically, because in this paper is also, we're going to focus on like order H term, which is like H being the amplitude, the typical amplitude of your wave. And in this paper, you have also coupling of the wave, between the wave and the velocity of spacecraft in the constellation, beta being the typical velocity of the spacecraft with respect to the solar system barycenter. Is basically 10 minus 4. It's normalized by C, so 10 minus 4 with respect to C, meaning that, yeah, this type of effect are basically to the 10 minus 4 level. So they could be important if like very loud source in LISA, but typically they're not critical. So we're going to focus on this part only. Okay. Now that's the hard part. Okay, so I'm going to explain a bit the setup. So here you see, so you have an emitting spacecraft here. So you're going to have spacecraft I and spacecraft J. Let's say that the spacecraft I is the one that emits the frequency. Spacecraft J is the one that receives the frequency. Both spacecraft follow a world line, time-like world lines, which is in blue here. And they exchange a photon, which is a null geodesics. And the straight line is this new geodesics if there was no wave. So it's one on an unperturbed background. And if you have this tiny perturbation, it gets this instead of this one. So we have a constant reception time because we are, as I said, we're sitting on the reception satellite, and the effect of the wave is going to be to delay the time when it was emitted. So you just change this reference frame, okay? That's why you see they receive at the same time, but if there's a wave, it means that the frequency you receive was actually emitted like slightly before or after. What else here? Yeah, so here's the D0 is the distance between emission and reception if your constellation was static, so there was no motion between the two satellites. This delta T0 is to account for the fact that during the emission, the light travel time, your both spacecraft have changed position, and possibly the arm lengths also have changed a little bit, so you add this new delta term. And the extra one is like due to the fact that the wave has changed slightly the time of propagation of your photon, and you have also an extra length due only to the wave, so the gravitational waves. Yes, so we're going to work in TT gauge as we saw yesterday, which means that in this gauge coordinate system, the world lines of two satellites are unaffected by the wave. What's affected is like the path in between emission and reception. Yes. Okay. Question so far?
The two blue lines are not covered.
No. Not necessarily. The slope is the velocity, basically. Yeah.
What's the delta t, small delta t?
This one?
In the bottom left.
This one here?
Yeah.
This is the extra travel time due to the wave deformation of the photon path.
The deformation
of the photon path. So the photon path between emission and reception is affected by anything that happened on the line of sight. One thing is like the relative velocity between the two spacecraft, because and the other thing is the wave. The gravitational wave is going to deform space-time in between the emission and reception, and can delay or advance the emission time with respect to the reception time.
So there are two photons, or just one?
No, just one.
It's
so
like
you follow one photon,
And then you
And
imagine...
the light travel time is going to be affected by the wave. It's going to stretch or compress the separation between position of emission and position of reception.
Because of the gravitational wave.
Yeah.
Okay.
This is the strain age.
But the photon is emitted at one place, not at... Like, it's just imagining
Right, but
that if
you,
it's...
okay, so exactly. So you sit at the reception spacecraft and you try to guess when the photon you receive was emitted. And this question depends on the relative velocity, but also the strain which perturb anything in between propagation. Yeah, this is a subtlety here. Yes, no.
One more question, please.
Yeah.
Okay, so if I understood correctly, the bottom red squiggly line is the path actually followed by the photon.
Yeah.
And then...
It's just an illustration, and it's
Okay.
yeah.
And then the other one is what you would guess from the receiving spacecraft if the space-time had no gravitational waves on it.
Yeah.
Ah, okay.
Yeah.
Okay.
Exactly.
So TE is emission, TR reception, and T0 is what we guess?
The time at which the photon received would have been emitted if you had an unperturbed background. That's what I say. An unperturbed background is like no gravitational waves, basically.
Does T0 always follow TE? Like, do you always guess that it's after, not before?
I think that gets modulated. It can depend on the... Yeah.
It can go both ways, okay.
Yeah. Yeah, and this notation, we're going to keep it. So we're going to have label quantities when you consider unperturbed background, so there was no wave, and deviation from this when there is a wave, and there's going to be a small one here. Okay. So let's start. So as I say, there's two reasons for the frequency you receive compared to the one emitted change. The first one is relative motion between SI and Sj. So this is orbital Doppler effect. It can be big. It's typically, correctly if I'm wrong, but I think it's basically megahertz variation of the initial frequency, which is terahertz. So it's much, much larger than the modulation to do the wave.
Yeah, a good order of magnitude is the relative velocity. The maximum relative velocity between the spacecraft and LISA is about 10 meters per second.
Yes.
So you divide by C.
I think 10 minus 6 we see or something like this. And the wave itself is like microhertz or something, I would say. So it's much smaller.
It's hundreds of nanohertz.
Yeah. So it's much smaller. But fortunately, this one is out of band. And the wave is in band, so that's why you can separate them, even if this one is much larger than the other one. And the second one is Kashmir lensing of the photon bath. So due to H, Tx. Yes. Okay. Yep.
Just so I understood.
The box.
Maybe you were going to write that down, but I just wanted to get an order of magnitude of all these numbers here. I guess C delta T is going to be the strain times the separate D naught, something like that. Or maybe not actually.
Yeah, so this is going to be order of the strain, exactly.
Times D naught, right?
The strain times L0. Yeah, dan D naught, exactly.
Time
Yeah,
D naught, okay.
yeah. More like L0 because L naught. Because this one is also, L naught is also, this one, excuse me, is also accounting for the fact that you have an emitter which moves respect to the receiver. But okay, that's okay, yes.
And delta D naught is going to be 10 meters per second times D naught by C. No.
No, 10 meters per second is the relative velocity
Yeah.
in the spacecraft.
Yeah.
Delta D naught is the distance traveled by the emitter spacecraft during the photon travel time, which is about 8 seconds.
Yes.
So it's more.
Okay.
Right. So yes. So to start with, we're going to express what. So give an expression of the observed frequency. So the frequency that observed by the spacecraft, which has certain velocity, and receiving a photon, which has a certain frequency. So this you can find. I think it's in. I could find this in Carroll's book. Sean Carroll's book, Spacetime and Geometry. I think you have like several equations, several places where this is mentioned. So I think you can also find it from simple Lorentz transformation. I didn't do the derivation, but so that being the velocity of the receiver, so the spacecraft, and that being the wave vector of the photon, which is received by the spacecraft. Yep. This one is a new. That's the frequency. Yeah. Yeah. Well, it's not a new. Yeah. So it's frequency. Yeah. Sorry. So it's going to be NDES. Yeah. Okay. Yeah. It's going. Hopefully, it's going to be clear. So this is a metric. So it depends on two things. It depends on the metric at which you do the observation. I mean, the geometry at the point in which you're doing the observation, and the velocity of the observer. You can also show that this, you can decompose it as a function of the tangent vector of your photon path, which basically determine like the geometry of the path between emission and reception at all lambda. So we're going to have this tangent vector define basically the path, and it's going to be function of a parameter which is going to help us to probe the different points between emission and reception. This is arbitrary parameters. It's just to travel along the geodesics. It's nothing parameters. It's arbitrary, but it's going to cancel out eventually at the end. So I'm going to bring that parameters along the derivation, but it's going to be canceling out when we're going to compare. We're going to build the relative frequency fluctuations.
Sorry.
Yep.
What does the N stand for?
Satellite. So it's either I or J. Yep. So just a label for the satellite. I kind of feel like we're gonna have not the time to go through all of this. So you that is also available in Endico anyway. Okay. So we're gonna try to go over the end. If you don't have time, you can check the full derivation. But please ask question. I think I prefer that. Yes. So you can prove that this frequency is actually. I'm going to explain what is nu zero here. You can decompose a metric between Minkowski and a perturbation of Minkowski, which is your wave. You keep your for velocity of your spacecraft, and you're going to introduce the tangent vector along your annual geodesics, which is a known, which is a function of lambda, the position in your geodesics. Nu zero is kind of like the natural frequency of your photon as observed from a co-moving frame, which you put at infinity, means a place where you have a flat spacetime. Okay, so this is the definition of nu zero here. Yeah, and we assume that nu zero is the same for the laser emitted by satellite I and the laser emitted by satellite J. We're going to see that it's not going to be the case, but let's assume this at the moment. Okay, then we're going to use TT gauge to simplify this further. So I'm writing super B. Okay, TT gauge you're going to help us simplify this term. So in TT gauge, you can show, as I said, that, well, I think I'm going to skip that. Yes, so basically H mu nu restricts to spatial component of the TT gauge. So the TT gauge, I'm going to use this system of coordinates. It's going to be time. It's going to be U and V, which are the polarization vectors, the direction of the polarization, and K, which is the coordinate along the propagation vector of the waves. Yes. And so restrict to spatial components, Ij, in this case UV, okay, UV. And so meaning that you can write HTT equal HTG equal HIT I and J between, well, okay, I could have put UV, but it's just spatial components. 0. Right, so you only have the components in U and V which are non-zero. Second thing, I think you can already write G mu more simply. So you can show that your metric G mu nu here can be write this way between the two spacecraft. Minus CPT square plus H plus X Q squared plus H plus TV squared Okay. You can even simplify this more because the source is typically very far away. So your wave, you can use very fairly the plane wave approximations, which basically means that. Yeah.
Can I ask a quick question?
Yeah, sure.
I think there's a subtlety that I missed out here. The spacecrafts are not in a Minkowskian thing with the perturbation, right? Because they're following geodesics based on the Earth-Sun system.
Yeah.
So are we assuming that manifold that is a Minkowski kind of a manifold, and on top of that we just have a simple H plus H cross? So in that case,
that's
so
what
we're doing a
yeah,
locality, right?
we forget about like solar system curvature and stuff.
Exactly. So, but
It's only introduced in relative velocity, so it's kind of introduced through that, but just at first order. So no, we have Minkowski plus H.
at the scale of 2 million, the distance between the spacecraft, that's a fair assumption to assume local.
Okay, maybe Tom can comment a bit on that, but yeah, I think the relative velocity is already capturing part of the effect, and in any case, that's a DC effect. So it's not in band anyway, right? Because the curvature aspects are.
Okay. Okay, I see what you mean. It doesn't change, of course. I think I see what you mean.
Like these curvature perturbations due to the solar system curvature are things that matter on like this yearly time span. So it's quite a long-lasting event, and the derivation we're doing here is just this 8-second window. So in this small time window you're taking, it's quite safe to just say, okay, I'm working on a Minkowski background, and you're not really feeling the effects of this, but you would have to adjust this D0 over time to account for the yearly flexing of the constellation. So it's in there, but it's captured in this D0 in this case.
Okay.
Yeah.
Because the relative velocity between the spacecraft, in a sense, is due to this curvature. Right?
Yeah.
Because otherwise it will be static. Okay, so then in plane wave approximation, can I erase? So I already write too big. Huh?
So where is H cross?
Good, that's a good point. Where is H cross here? I missed it. I missed it. I missed it. Yeah. You saved H cross. Thank you, Claire. Yep. Thanks. Yes, and okay, and then plane wave approximation. You don't need to write anything. I put the notes online, so no worries about writing. Plane wave approximation. Gonna have this. It's actually reduced to only a parameters, which is the retarded time. And I think I have a video. I think it's obvious when you see that here. Yes. So you basically have the only coordinate where the phase change of your wave is going to be along the propagation. So it's going to be retarded time here. So a combination of t and the propagation direction coordinate. So basically the strain depends only on that coordinate. So because of that, you can write the metric even simpler. Maybe I read that. Maybe I can write that also. Yeah, maybe I'm going to just write the metric matrix. I'm going to get that. So we're now switching to the light ray coordinates. It's going to be psi, eta, u, and v. Psi being ct minus k, and eta being the advance time ct plus k. Okay, and in that coordinate system, G mu is going to be 0 minus 1 over 2 minus 1 over 2, 0, and plus h plus 1 minus h plus, going to depend on psi. H cross depending on sky. Whoop. I need to take more. H cross psi. Only. And then 0. This is psi, this is eta, this is u, and this is v. Right, okay. Okay, so if this is the case, then now you can write un, simplify by the fact that you have many terms which are 0 in this metric. And so your un can be written this way. So you keep that part. But now, the one that coupled to velocity is simply yes. So you have only the spatial component here. This gamma is a Lorentz factor. It's just because you decompose the for velocity into the time and spatial components. It's just a factor when inside your for velocity. Okay, so at this stage now we're gonna use this decomposition between a perturbed background and an unperturbed background, so Minkowski plus this H. And we're going to say that beta is a velocity. It's a boost factor. You know, it's a V over C. Yeah. So you have basically nu is equal to gamma C V.
And what is sigma?
Sigma is a tangent vector. So this is who's asking? You're asking. So it's a tangent vector.
Tangent vector?
Yeah. So this is this vector here. So this is a tangent vector of the geodesics.
Photon.
Yes, a photon path. Exactly. But it's also a quadrivector with time component and spatial component. So it's very defined as the direction of the photon as it progresses between the two spacecraft. Okay. So then, if we decompose now, so we're going to systematically decompose all the quantity between an unperturbed background. So one you would have is to have no wave, and a perturbed one, so the correction due to the wave, and plus anything which is nonlinear in H, which is going to fairly neglect. Typically, this is 10 to the minus 18 for Lisa. So H squared is going to be 10 to the minus 36. Yes, so if you plug that into this and decompose this thing, this becomes mu n minus 2 0 c plus c. Yeah, so again there is a inconsistency. I'm going to explain it later. Plus plus so you just decompose the sigma dots into a not version and a one version. Plus this guy here, gamma beta I, sigma dot G1. Okay. And the trick here is that this one is of order beta H, because you have an H and you have also a beta which is already small. So we're gonna.
Your sigma 1 is at zeroth order or first order in H?
Sigma 1 is first order in H, yeah.
Yeah, so in any case, I
Beta
think it's
is
even
first,
beta H
yeah.
squared. Yeah, indeed. Yeah, so it's even better. Yes, so you're gonna end up.
I think when you say beta TT, that's coordinate 0.
Yes, of the Minkowski metric. Yeah. And then you're gonna have the final equation for the frequency.
Okay.
I'm not sure we're gonna be able to elaborate more.
That's what you want to describe.
Gamma mu 0 over C. T plus yes, and that's the final equation. So in this equation, you have three terms.
Sorry.
Yeah.
Nu n
The frequency observed from the point of view of one of the satellites,
but
either
so,
emitter or receiver.
okay, so one is emitted and the other
Yeah.
is
So
received.
mu I is emitting and then mu j is receiving.
Yeah, exactly. Yeah.
Why is mu I affected? Like,
Because
why
of
are both
relative-
of them affected by the gravity?
by your local geometry.
I guess I'm going to take the difference and then.
Yeah, exactly. So the final observable is going to be mu I minus mu j over mu I,
Sure.
and that's going to be the frequency fluctuation due to the wave.
Okay.
And that's the one you're going to compose with TDI. Yes.
The sigma are still. The sigma are still parameterized by lambda, right?
Yes. At this stage, yes. And actually, the dot is excuse me, I should have specified this. Sigma dot means
With respect to
lambda.
lambda.
Yeah.
Yeah.
To use any arbitrary parameters that help you to travel along the geodesic.
Yeah, but
You can identify lambda with certain parameters. We can what we're going to do at the very end, we can identify lambda with psi actually, because that's where it's not arbitrary in our case because we do exactly what you said. So mu I minus mu j over mu I, lambda will cancel anyway, and the end result should not be depending on the actual choice for lambda.
But lambda is fixed when you say, for example, when you apply your final equation for nu I, then you have to pick a lambda, a specific lambda for your sigmas.
So I guess it's gonna affect the gauge, the form of your sigma, so all the components and the way it's the gauge choice for sigma.
Yeah, the problem here.
The problem here is that sigma is a null geodesic, and null geodesics use affine parameters, so it's not necessarily a time, it's just some random thing you assign to be the affine parameter, and this is invariant under rescaling and picking translation, so essentially picking boundary points, and you have some freedom in there, but in the end, if you calculate this response, so compare these frequencies, these choices cancel, so this choice of affine parameter doesn't matter in the end.
Okay, agreed, but
Yeah.
what I meant is, for example, if you choose your bounds to be 0 and 1 for lambda,
Yes.
0 at j and 1 at
Yeah.
I,
Yeah.
if you want to write sigma I, then you have to apply lambda equals 0 or 1.
But you need to take the when you switch to first order and H, you have to adjust your boundary conditions in that point. So the parameterization at 0th order and first order will be different in that case. If you decide to fix your boundary points at 0 and 1.
Okay.
Yeah.
Thanks, Tom. Okay. So a quick interpretation of this term. So this guy is going to be constant, and it's going to cancel out when you combine mu I minus mu j. It's going to be constant over the geodesic. This one is where you get your h. This is really this one that measures h. And this one is a DC Doppler term. So this is this megahertz modulation. Okay. But in a case where we neglecting beta h square and also beta h, everything is contained in there. I don't have much time. Maybe I can only show. So how would we constrain sigma? So we're going to make use of the particular symmetry of your metric, which, as I said, depend only on one parameter, which is the retarded time. And because of that, all the coordinates, your coordinates which have no incidence on the metric, like where you have the symmetry, you can find killing vectors for them. And these killing vectors are associated with constant of motion along the geodesic. So you're going to have three equations to constrain the geodesics, which are due to this constant of motion, plus a fourth one, which is due to the fact that you have a null geodesics, which means that the contraction of G and your sigma is going to be 0. So you're going to have 4 constraints. And with that, but this is exactly what you see here, actually, on the left. So, yes, you see that because of this, maybe I can just show the killing vectors things. Let me erase there. Yes. All right. Yes, so because of this, because G depending only on psi, we have 3 killing vectors. This one, which basically a Kronecker delta projecting quantities along this U coordinate here. Okay. Continue is equal to V this time, because it's also independent on V, and this guy here. Right. And so you can show that because you have these 3 killing vectors, you have 3 constants of motion. I'm going to call alpha I. Show this. They are conserved along the geodesics, so they're independent of lambda. Alpha are independent of lambda. And so doing the math, like computing the project, so I can be 1, 2, 3. These are the 3 constants of motion. You end up with these equations here, which fully constrain the new geodesics between emission and reception. And the trick we do is we will again split into an unperturbed quantities and a perturbed quantity at linear order, and we have 2 sets of equations. The first one, you see that basically all your tangent, the components of your tangent vectors are constant, which means that you have a straight line. And the second one, you see appearing the H strain term, and there's a bit of algebra you can find in my notes. I'm not going to go through it here because no time is mostly calculatory. But you can show. You can solve that, integrating them, and finally get the expression of nu as a function of the strain. Yes, maybe I can just show you the last expression. If I have it somewhere. Yeah. Okay, so once you have the expression for nu n, and you know the expression of this nu dot because you solve the constant equations, then you can compare nu I and nu j. Here I'm noted them nu reception and nu emission, they're the same. And you divide them by nu emission, and you get your relative frequency fluctuation, which are laser observables, from which you're going to construct the TDI channels. Okay, and so okay, so I'll spare you with the details, but at the end of the day, you have this formula here, which are the frequency fluctuation of the emitted frequencies due to the wave. This is called the 2-pulse response, because it's basically proportional. I mean, it's projected. You have geometry terms. These are projected this strain, but at the strain evaluated at emission, at reception, and at emission. So you're really sensitive to these 2 points. Plus a Doppler. So this is the relative velocity between the 2 space frames. Yes, and so the classical laser response. We did all that because there was another derivation, but which is a bit more simple, but which was making a crude approximation, considering that the geometrical path between emission and reception of a photon was straight. And if you neglect the velocity of the satellite, it's fine. But as long as you want to also account for coupling between the velocity of the spacecraft and the strain, this leads to error. So this one is a bit more technical, like involving Killing vectors and things, and frequencies. But at the end of the day, it's more robust and you can derive more terms. That's exactly what's in our paper. Yes, I think the first one is incorrect, actually. Yes. Yeah. Okay. So let's stop here for the math. Again, I think you find everything here. I'm going to find the full derivation here, if you're interested. Yes. Okay. And then okay. So now that you have this, we're able to have a prediction for the comparison between the emitted frequency and the received one. I can tell you that this mu0 is actually not the same for the emission and the reception because, as I said, we're doing interodite interferometries. So the frequencies are slightly different. And what you're going to be sensitive to is the beating node between the two frequencies, which got again modulated by the difference in frequencies, including the effect of the wave. So basically, in interodite interferometry, so you combine two frequencies which are close enough, and combining these two frequencies, let's say you have a course of a first frequency and a sinusoid of a second frequency. If you combine them, you get this trigonometry relationship where it's actually a product of the sum of the two plus the difference, or times the difference. And so this is going to modulate a higher, like a much higher tone. And in LISA, we're going to be sensitive to the modulation between the frequencies here, and that's where the gradation wave is going to hide itself. Okay, it's going to be even more striking when I do the. So I converted everything in sounds.
Maybe just the order of magnitude to understand why we're only sensitive to the difference is that nu1 and nu2, they're of the order of, these are optical laser frequencies.
To terahertz.
So they're hundreds of terahertz.
So is it a choice, like this interodite interferometry, because you want to listen to it, or is it like due to the fact that you space and it's harder?
I guess okay, so it's very classical, interodite interferometry, so this is very widely used. And I guess also it's the case, right? Because, I mean, it's very hard to have the same frequency because of all the Doppler effects and things. So in any case, you won't have similar frequencies. No. No. Sorry? So it's intensity interferometry, so they have like a fringe. So it's the same frequency that go on left and right.
Yeah.
And then, so they combine the two and they work close to the dark fringe. So they're sensitive to intensity. So intensity is observable.
Okay.
In our case, this is a phase of the beating node. So it's very different.
Okay.
Yeah.
Okay, just to make sure I understand the logic of the measurement here, you were showing this single link response, which is this Y quantity.
Yeah.
So it's a relative difference between frequencies. Is this what is actually being measured?
Yes, because the beat note, as you see here, when you combine the two signals, you get two components of signals. You get like the sum of frequency. This is this very fast modulation. And you get this envelope. And the envelope is the difference of frequencies. And that you can measure the timing of this envelope, the phase modulation, and that's exactly what we measure.
Okay, so
we're tracking the phase of this envelope modulation.
Okay, so this. What you're showing here is not what we do on top of those. You're showing the logic of how we actually measure
the relative frequency, exactly.
The relative frequency, okay.
It's going to be this envelope, and the phase modulation of this envelope going to contain the wave. I think it's going to be immediate when you hear the sound. So you have a first frequency. Okay, a second one slightly lower. And now you combine the two. So you see a beat. And this one is like the modulation. So you have another frequency, which is the difference between the two.
Okay, so the spacecraft is measuring these beats, exactly. And that's what it's returning to you.
So you're going to have interference across the constellation, and it's going to measure this beat, and you're going to phase meter, which is going to measures the phase modulation of this bit.
Okay, and in reality, these reference frequencies are terahertz, I suppose, because it's optical.
The high frequency part is terahertz, but this bit here, so you're going to have several bits, not only one. So you're going to have the modulation due to Doppler effect. So this is going to be megahertz, and the wave is going to be, we said, microhertz. Yeah, so if you have the wave, okay, same. Here you have no noise, so of course you hear it. If you beat the two, but on top of that you also have the wave. There you go. And now you do the same, but you add noise between the two. So on top of this frequency you have also large frequency noise. And here's what you get. One, and the big thing is that it's a bit noisy. But so you combine the two, and when at the combination, the frequency get cancelled, and you're left with the modulation between the two frequency, which contains the Gaussian strain, the effect of the wave. Here, in practice, so two frequencies you're going to combine, so they're not going to have the same noise relation, or at least they're going to have a noise relation, but it's going to be delayed. So the noise is not going to be in phase. So that's why you're going to need to delay the data streams in order to have coherent noise, and that indeed, when you combine them, they cancel out, and you lead with a bit of noise.
Sorry, just a naive question. So is the instrument only sensitive to the beat note, like to the envelope, or can it also detect the
super high frequency part?
Yeah.
But I think the point is really to measure the phase modulation.
Okay.
There's no point in.
Okay, so you don't care about whatever's going on under the envelope. Okay. Okay.
So
Sure. Sure.
What is this common noise that you're cancelling out by? What is that
So
correlated
here,
noise?
it's a little experiment. I add the same noise on U1 and U2. I combine, and of course, this term here. They have the exact same frequency noise, so the noise cancel out here, but not here. So that's why you see this beating of the noise as well, the noise beat as well.
But in reality, like, what is the actual source
in
of
reality,
common noise? Is it like the fact that it's not in one spacecraft also?
Exactly. So in reality, you need to compose exactly this, but on ground, that's TDI. So
that's the X and Y.
Because the noise is not going to be in phase when you combine the frequencies, because some of the noise is going to travel a bit more. Pass between the two spacecraft. But if you apply cleverly the delay between all your data streams, you're going to be able to keep the noise coherent so that they get suppressed when you combine things. That's the idea of CDI. Yeah. In a notebook, you can flash the code, and I made a notebook where I introduce a delay between the noise, so it's a very simple setup. So imagine you have, the setup is like this. So you have one spacecraft, two frequencies, so U1 and U2, which travels and come back. They pick the wave, so it's not like LISA. But there is a common noise between the two frequencies, but one arm is much longer than the others. So when you recombine, the noise is not in phase. And the exercise is you need to synchronize, delay properly, so that the noise gets cancelled, and then you get, it's a very different setup, but you get an idea how TDI is working. So you can have a look at this.
But I think Raoul was asking what is the physical origin of the noise?
So this is the fact that the frequency of a laser is unstable.
Okay.
So it changes with time. And this change is much higher than the modulation due to the wave.
But you're talking about two different emitters, right? So So
we have two frequency per spacecraft, right? You have two lasers per spacecraft, and they all have their own frequency fluctuations.
Okay. Maybe I'll talk.
Yes?
Sorry, so I know You okay? So yeah, so what you were saying is because even though they're two different lasers, so they would have the same type of noise, so they still cancel out that way, even though it's not directly the same source.
No, here I think it's a very simple setup. It's not representative to LISA. But, well, maybe Jean-Baptiste can answer more on that, but I think that the lasers are locked, right, with each other, so that they share the same noise.
So there are a couple of things, but even without talking about locking, yes, the laser noises are different on different spacecraft, so they're not coherent.
Mm-hmm.
So you could not really do this,
Mm.
but we don't make a single measurement on board the spacecraft, as Henri said. We have multiple interferometric measurements, and it turns out that we're measuring the same noises multiple times, so that there exists combinations in which those cancel out.
Okay.
So here.
For example, in a single spacecraft, you have two lasers, but you have an interface between the two lasers only, so you measure the noise with respect to each other, and that participates with your constellation of measurements that you need to post-process in order to suppress everything at the end.
It's a bit like if you have a room with two people speaking, if you have a single mic, it doesn't work. You cannot like remove one of the persons. But if you have two mics at two different places, so that the speeches have different time correlations in your recordings, then you can align correctly your two mic recordings such that you can wipe out somebody's speech. It's the same.
Okay, all right, what's next? No, you don't want this? Yes, okay, so here, just a picture. Yeah, this is typical, I think I took the wrong picture. In a notebook, you have the same plot, but given in terms of Doppler shift. But this is relative velocity between the spacecraft. Right, so this is between spacecraft 1, spacecraft 2, 3, 2, and 1, 3. And you have typically like a modulation of 3 kilometers per hour. This is over 10 years. And so this introduces a megahertz modulation of your frequencies that you need to account for. So that's why also, because when you do interior interferometry, you want to keep a working point of a certain difference between the two frequencies you're combining. If they're too far away, that could affect your sensitivity. So you want to make sure the frequencies are like roughly in average are distant from a constant. I mean, there's a constant delta between the two frequencies. But because of this modulation, which is due to orbits, you can go over that range. So there is a whole frequency plan that accommodate for the orbits to make sure that this delta nu from which you're building the interference is roughly constant. Okay, so the frequency of the working frequency of all the lasers in the constellation is evolving with time to have this constant range for heterodyne frequencies. What else? Yes, no, I think that's it. Okay. Yes, so that we discussed already. So the idea is like to compose, so you have a set of measurements across the constellation. Here I'm just showing so interspacecraft bit nodes, so the one that exactly this one to which I derive on Blackboard. But as Jean-Baptiste said, you have also measurement between test mass and spacecraft to measure the noisy motion of the spacecraft relative to test mass. This is also a frequency. And you have also some frequency between, some reference interferometer between laser only, so that you can measure the frequency noise. And then you combine all that, and you're able to suppress the laser noise efficiently. You're going to have a specific topic on that on Friday, of course. Yes. Okay, so maybe, yeah, I forgot about this. Maybe the last 10 minutes about more dynamics aspect of the constellation. So for now, we neglected totally the fact that the spacecraft was also noisy in its motion. So you have a noisy motion of the spacecraft which is in band. So you need also to account for this. So the Doppler term, which due to orbit is not in band, but the fact that you have solar noise pushing the spacecraft, or oscillating the spacecraft, and also the whole thrust system of the spacecraft, also making it shaking. This noise is in band and can induce a frequency shift which can compete with the wave. So that you need to be careful about. And so that's why we have on board 2 test masses. So they're in vacuum chamber, as I said. So they're protected from external force noise. There are some interaction with spacecraft, but they are mitigated as much as possible. And so there is a wall control strategy to make sure they're all centered in the housing, because if they're drifting too far away, first they can hit the wall, which is bad. You don't want that to happen. And also they need to work close to working point to the center of the housing, because that's where you have the least gradient, electrostatic gradient, and also gravitational gradient, so that you minimize the force which are actually applied on test mass. So there are 3 types of control of this system. So this is a 3-body system, even more because the MOSA, the telescope, can also rotate like this to make sure that you're pointing towards a distant spacecraft, because the constellation is flexing a bit. It's not a purely equilateral triangle. This triangle is flexing. Yes, so you have 4 control systems. One called the attitude control. So you need to make sure that the spacecraft is oriented well, so that it points towards the distant spacecraft. So you have a control of the overall orientation of the satellite, and a control as well of the opening angle of your MOSA. Okay. So typically, when you see the control strategy, is typically when you see that both MOSA deviate at the same time, it means that you need to actuate the satellite itself to correct it back. But if you see that one is well aligned compared to the incoming beam, and one is deviating, it means that the 2 MOSA needs to rotate. Okay, so you always have a differential mode and a command mode. Command mode, you act on the spacecraft. Differential mode, you act on the telescope independently. Drive free control is so you're able to. So you have an optical metrology. Maybe it's better if I use this one here. Yes, it's bigger. So you have a set of sensors or boards which track really the motion of the test masses. We have optical metrology system along the 2 line of sight of the telescopes. And these are very precise metrology systems, so they can track the test mass motion up to picometer level, per square root level, on both axes, which means that basically on these 2 degrees of freedom, if you lock the spacecraft on these 2 measurements, you can have a very stable spacecraft in that plane, in both directions, because they're locked really on the test mass motion, which are protected from acceleration noise. So the spacecraft is super stable in that plane. For the other degree of freedom, you don't have optical system, so you have a bit less precise system, which are a set of electrodes surrounding the test masses, with which you apply some voltage. If there is imbalance of a controlled imbalance of the voltage, you can apply a force translating the test mass right or left, up or down, and also rotate it. If you do an asymmetric imbalance between the electrodes, you can actually apply torques and make it rotate. As I said multiple times, you certainly don't want to apply any force on the axis here. But as I said, because you have optical metrology system here and here, and also if you see, let's say, on this axis and this axis, you never apply any force on test mass, but you can actually translate the spacecraft. You can correct any motion seen by the 2 test masses. How the control works is, again, you can correlate the motion observed by the 2 test masses. If you see a common motion, let's say that both test masses go that direction, it probably means that something's happening to the spacecraft, and you can thrust the spacecraft to correct both test masses at the same time. So this is drag-free, but sometimes you see, because of especially gravitational interaction between the spacecraft and the test mass, this is one of the major sources of noise. Actually, it's crazy to see like you have 1-ton spacecraft that can generate an appreciable gravity field for the test mass. So this can cause a drift between the 2 test mass, and in that case, you cannot correct that with the motion of the spacecraft, right? You need to do something and apply force on test masses. We are allowed to do that, but we're going to do that only using the y-axis. And you can show that applying force only on the y-axis and correcting the rest with the spacecraft, you're able to control all the degree of freedom of your system. Okay, so that's the strategy. Whenever. Yes. Yeah. Sure.
Is this correction done by the spacecraft control on the ground, or does the spacecraft do it itself?
It's doing it on its own. Yes. So you have a control system. Like whenever you see motion here, it reacts automatically.
Okay.
Yes.
Okay, again, just to see if I understand the basics. So each spacecraft has two optical benches, two Moses.
Yes.
These Moses, they can move independently. Each one has its own test mass.
So that is not clear. I think the scheme for controlling this thing is you act only on the opening angle. So you do that symmetrically, coherently between the two Moses. Because you can say, well, actually, I'm not sure. Ricardo, maybe you can answer to that. Do you remember? You're still discussing it. Okay. But we're going to have several control strategy. In Pathfinder, it was the same also. Like you have a science mode, you have like an acquisition mode, you have like a safe mode, you have like acceleration mode, and so on. Depending on the mode, you're going to enable some degree of freedom of control. So the science mode is going to be the overall opening angle is going to be actuated at the same time, and for the rest, you're going to rotate the spacecraft, and that's enough.
Okay, I just want to understand what the target is. So you're trying to keep the spacecraft around the two test masses without touching the test masses, without interfering too much on their inertial motion, at the same time as you align the telescopes with the other spacecraft. That's it?
Here, yes, just a comment. Here it's a bit confusing. The rotation point of the MOSA is going to be the center of test mass. It's important, because otherwise you're going to have a lever arm. And so the rotation point is at the center. So if you rotate the MOSA, you don't translate the test mass.
Okay.
The MOSA being the telescope, excuse me, movable optical system assembly, subsystem assembly. So it's a proxy for the telescope, but it contains also the test mass, optical bench, and all the apparatus.
Okay.
Very quickly. So those are gas thrusters, I guess.
Yes, cold gas thruster. Yes.
Is that what limits the observation time for LISA?
Yes, partly yes. Partly yes, because you take on board like a limited amount of it. I guess this is what limits the 10 years, no? 10 years duration are limited to that. So the nominal is 4 years. Every single way is going to be extended to 10 years, acceleration to up to 10 years.
Mm-hmm.
And actually the final limitation is cold gas. Yes.
Just take some more, guys.
Give us more money.
Is it that expensive?
I mean, the more kilo...
Weight and volume, yeah.
What else? I think we're getting close to the end. Yes.
Yeah.
Okay. Yeah, I think I can stop here. You're gonna have more detail about all the TI things on Friday, and I'm not sure we're gonna do the hands-on session. Maybe next week, if we don't, just have a look, play with the sounds and stuff, like trying to recover the bit note. I think it's fun to play with this notebook. Yep. That's it. Thank you.
I mean, we already had some questions, but we have maybe time for one final question, if there's any. No? Okay. Well, then we have the break, and we'll reconvene in about 15 to 20 minutes. Remember, don't bring any drinks on the room, right?